bodies of water. So it doesn't apply to water in your toilet. Because some people say, well, go and see kind of the direction water is spinning in your toilet, and then you can know which hemisphere you're in. There's something to that. In the northern hemisphere, this sort of deflection is going to be what we say to the right, and the southern hemisphere, it's to the left. And it has to do with the spinning Earth, just like we said. Put another way, if you were a jet, I kind of like this way I learned it. If you were a jet, you leave the Earth's surface, and you're going to try to along a line of, let's see, this would be what, a longitude. You're trying to get to A. Well, if the Earth's not spinning, you're going to get to A. But since the Earth is spinning, you try to get to A, and the Earth is spinning underneath you because you're in the air. So actually, you end up at B. Okay? So that's, to me, kind of an easier way to think of it. Okay? So that's the deflection that we're talking about. And it is to the right in the northern hemisphere and to the left in the southern hemisphere. Only affects large bodies of water and air. Air also has this little kind of tweak to the right. Coriolis force is strongest at the poles, and at the equator it's basically zero, which has consequences for hurricanes, the part that we're not going to talk about. But so this actually was one of the things you got to in your lab that you guys did on last Thursday, was whenever you see an H on a weather map, okay, that would be a surface high, central high. We call those H's anticyclones. Anticyclone sounds scary, right? But it's not, okay? Around a high pressures usually are kind of blobby because, you know, we look for a bullseye kind of with regard to the pressures around the central system. But highs are kind of blobby. They have a low gradient. They're wimpy gradient. And the Coriolis force will make actually around a high, you should look for wind going clockwise. Which actually makes sense if you look at the North Pole, you guys would tell me the Earth is spinning counterclockwise, like we talked in astronomy. And so anticyclone clockwise in the northern hemisphere, because that's I think where it came from. So from a high pressure, and this kind of goes back to what I started out with, air generally wants to move from a high to a low, so we have this air moving out from a high. That's like the kid who threw up. He ate too much candy and he threw up. That's diverging air. Okay? So if it's diverging air, it's not going to go up there. It's going to actually, you're going to have a column of air moving down. And that's why you end up with kind of nice, warm, usually clear skies with this descending air, column of air moving down from upper elevations. So, anticyclones, I'm all for them. Okay? They bring clear skies and warm conditions. All right. So the opposite of an anticyclone is a cyclone. So if you're a Iowa State fan, you know, you're familiar with this whole idea of cyclone. And when we talk about severe weather, we're going to see that they are in, sometimes we call cyclones, tornado cyclones. And there's a reason for that, because they actually have a low pressure in the center. The thing about, if you see a weather map with those, we call them isobars, those lines that mark the same pressure, and it's a low, you're going to see them nice and tight. And if you see them tightly spaced, that means you're going to get some wind. The thing, and again, we kind of have some yings and yangs. Highs are anticyclones, or lows are cyclones. So with cyclones then, we're going to have air moving counterclockwise, kind of like it does in the northern hemisphere. We talked about throwing candy out to a bunch of kids on a playground, and they're all going to kind of bump heads to get to the candy. We have converging hits. We have converging air with a low because it's all kind of high outside. It's coming together, and it comes together and it squishes, and actually it's going to move up. And anytime you can get air moving up, you can get it to expand and cool and create clouds. So we think of central low pressures on a weather map, cyclones. We should kind of look for generally cloudy skies, maybe some strong wind because of those tight isobars. and relatively cool conditions. So those are, generally speaking, kind of what you got going on there. Okay. So let's see how far we get here. Got too many papers. All right, like I said, there are several slides in here, or topics in here, that I'm going to tell you to go ahead and skip this semester. One of the things about winds is winds are always created as air is going from a high, dense air particles to a low pressure, loose air particles. Okay, high to low creates wind. And the closer, the more drastic the change between the pressures, the stronger the wind. We talked about how you can actually get some sort of different sort of pockets of high and low pressure here on Earth. The greater the difference, and it's kind of like, to me, when you're talking about a topographical map, or one that has the elevations. You know, if I put those marks of elevation close together, you know that if you step a little bit, you're taking a big drop. It's the same thing with what we call isobars. When we use isobars to kind of connect locations of the same pressure. Okay, so I'm going to talk about 3 different scales of winds, and the large winds are going to be pretty large, but there's even larger than that. So large winds would be the size of several states, and those would be affected by CF, stands for Coriolis force. CF stands for Coriolis force. I'll put it up here. Sometimes called Coriolis effect. Okay, 3 scales of wind, and they're based upon how big they are and how long they last. So here they are. So these are adorable. This little gust of wind is picking up these little newspapers. Okay, wind gusts. How long do they last? Seconds to minutes. Dust devils would fall into that category. Who doesn't love a good dust devil? You're like, well, that's pretty cool, right? But any wind, whether it's a dust devil or this, is actually air relocating from a high to a low pressure. These are what we call microscale winds. Okay, something a little bit larger and lasting a little bit longer. Mesoscale wind patterns. Of course, we have a picture of a tornado. Meso meaning kind of middle. Okay, they are larger and last longer. One of the topics we're not going to cover is this idea of kind of what we call local breezes. And I'm going to skip it on the next few slides, but if you've ever been in Chicago in about 3 o'clock, depending upon what the other weather is, usually more a sunny day than a not sunny day, but you get these kind of winds coming in, and it's coming off of Lake Michigan actually, and that's a local wind pattern. So here, of course, you picture this hurricane. Okay, this would be a large scale. There's even larger scales than a hurricane with regard to weather patterns. So they're larger and they last longer. How large are they? Planetary scale. Okay, that's a large wind. And how long do they last? You know, weeks, months. They're just always there. A little bit smaller than a planetary scale would be synoptic scale. Okay, and these are synoptic scale, planetary scale, and macro scale. So we have micro, meso, and macro scale. Kind of small, medium, and large winds. How big they are and how long they last. So if you want to take the next 4 slides, you can go ahead and mark an X through them. Skip the next 4 slides. And one of them is talking about the Chicago wind, the what we call a lake breeze. Let's see if that should bring you up to here. And actually, I'm going to go ahead and kick this topic off with a video. See what we think. So I almost say 6. This is where I start to fuss a little bit. I'm like, They say 3 cells. Well, actually, there's 3 cells in the northern hemisphere and 3 cells in the southern hemisphere. So 3 plus 3 is 6. And one of them is the Hadley cell. Okay? So what we saw in the video was kind of the wandering hotspot. And let's see, how would I say this? This, I feel like it's something we talked about in astronomy, the seasons. Okay? We said, I have a big globe back there, but I don't want that big globe. If this is the Earth's axis of rotation, and here's the sun again, right? And that's north, and that's Polaris. So here you would say it's summertime in the northern hemisphere. And as this works out, actually, the hot spot isn't at the equator. The hot spot actually is about what we call the Tropic of Cancer. That's the hot spot on the summer solstice. Okay. Going here 6 months later, the winter solstice in the northern hemisphere, the hot spot is not at the equator. The hot spot is 23 1/3 degrees south. That's the Tropic of Capricorn. So we kind of have this wandering hot spot. Okay, so that's kind of what that's saying. Okay, the Hadley cell is closest. I think I'm going to make this little diagram here. Ferrel cell, that's us. We're about 45. So 45, and these are lines of latitude from the equator. So we're about 45, that's between 30 and 60, and then we have the polar cell. So it kind of looks like this, and you'll see a better diagram coming up. But if I were going to just kind of show that, and I'm not going to worry about the wandering hotspot right now, it would look like this, where here's my 90, my equator. Of course, that's 0 degrees Celsius, 0 degrees latitude. I'm going to go ahead and split this in thirdsies. Okay, well, if this is 90, thirdsies looks like this, where we have 30 and 60. Okay, and then we have Hadley, Ferrel, that's us, we're Ferrel, and polar. And do you see where I say there's really 6, because actually we have a Hadley here, and we have a Ferrel here, and we have a polar here. So anyway, there's really 6. So how does that work? This is a figure that's a little fancier than what I drew. It's a little more complicated, but you can see the sectioning. You can see the 3 sections in the northern hemisphere and the 3 sections in the southern hemisphere. And you can see the names I use. So we have Hadley, Ferrel, but I don't know, I never spell Ferrel right. And polar, okay? It's a little complicated. Oftentimes when we're talking about global winds like this, you'll kind of see, somebody tries to show you 3 dimensions. You can see kind of the arrows on the flat globe, but maybe you can also kind of see these arrows that are going kind of in the atmosphere. All right. So air flowing in these cells generally move vertically at the edges and horizontal between the edges. Vertically at the edges. Well, what does vertical mean? Straight up and down. So can you kind of see this? And actually, a good place to start when trying to unravel this is like what the video said, that hot spot that's not always at the equator, it wanders a little bit. There's that hot spot. Did I ever get that out? Dropped. Oh well, maybe it'll show up. What I was trying to do is to kind of emphasize this air rising, just like it rises in your house. Air rising here. Well, it bumps up against the top. Let's see, we are in the troposphere. What's on the top of the troposphere is what we call the tropopause. So actually, it kind of bumps up against that, and it flattens out, and it goes, some goes north and some goes south. The stuff going north is part of the Hadley cell in the northern hemisphere. The stuff going south is part of the Hadley cell in the southern hemisphere. Okay, so yeah, they're confined to this layer of the Earth's atmosphere, which we know is the troposphere. That's where weather is generally. Okay. clouds are. All right, so that hot spot, we can't just keep calling the hot spot. That sounds so unscientific. So that hot spot actually is going to be called the ITCZ, all caps. I stands for intertropical, C stands for convergent, IT stands for intertropical, C stands for convergent, and Z stands for zone, intertropical convergent zone. So we kind of think here at this would be your ITCZ, intertropical convergent zone. That's where air is rising, and the air is rising because it's hot there, and kind of as a consequence or related to that, we kind of have air at the surface coming from the north and from the south along the Earth's surface and then rising up. That's the convergence part. This is showing you the wandering, and I hope this makes sense. Okay, the words are north and south. So you guys would tell me that if the northern hemisphere is experiencing summertime, then like I told you a minute ago, the hot spot's going to be in the northern hemisphere. So in the wintertime, the hot spot's going to be in the southern hemisphere. So the ITCZ, the intertropical convergence zone, wanders throughout the year. The other thing is, and we have to do this in science. We kind of simplify things, and then we have to talk about more about details. But as I've drawn it here, the ITCZ, intertropical convergence zone, is not only at the equator, but it's straight, and that's not the case. Okay, you can see it's not even straight. And the fact that it wiggles and stuff actually has to do with it's related to kind of how land and water heat up differently to kind of give you some different. Okay. So that rising air cannot just like escape Earth's gravity. That rising air is actually going to bump up against the top of the layer of the atmosphere that's closest to the Earth. So it bumps up against what we call the tropopause, which is the top of the troposphere. It's like a lid. And some's going to go north and some's going to go south. Well, let's just focus on the northern hemisphere. We're not going to talk about all 6 cells. I just want to talk about these 3 cells, okay, a little bit, and then you kind of have to, or you can go ahead and say they happen in the southern hemisphere too. So, air at the upper elevations, and I think the video kind of talked about this. The way I look at it is when it, see, this is my, oh, okay. When the ring of air, okay, so my hot spot would be around my equator. Okay, that air rises, the tropical convergence zone, hits the tropopause, and part of it goes this way, and of course part of it goes this way. We're worried about this guy. Now, as it goes about 30 degrees, actually, it's kind of got a ring of air that used to be this big, and now it's this big. So that ring of air is kind of bunched up, and actually that ring of air descends about 30. And that finishes what we call the Hadley cell. Okay, so we have descending air. Now, one of the things about descending air, I said a little bit ago that descending air actually is associated with a high pressure. And with high pressure, we have clear, high central anticyclones, no clouds, warm. It's related to actually air that's going down will not cool, air that's going down will warm. So about 30 degrees latitude in both hemispheres is kind of where we have some of these most arid sort of dry desert conditions. So anyway, that's the end of the Hadley cell. What else we got? So this is kind of showing you, let's kind of get our bearings here. The green is the hot spot, the intertropical convergence zone. This is the northern hemisphere, the southern hemisphere. We have this rising air. Anytime air rises, it will expand and cool. Actually, this is where we have our, if you're into climates, this is where we're going to have our nice rainy conditions. It's going to hit the tropopause. It's going to go both ways. It's going to kind of bunch up and start to descend about 30 north and 30 south. Okay. Now, this descending air is dry and warm. So the words were north and south. So when we talk about cells, we kind of have to finish our cells. So we just have that descending air, when it hits the Earth's surface, some's going to go north and some's going to go south. And the stuff that goes south back towards the intertropical convergence zone finishes that Hadley cell there. This stuff that's going actually north, that's going to begin the other cell. That's going to begin our second cell, our Farrell cell. So yeah, potential for the word is deserts there. There are other reasons why we get our different climates, but this is one of them. And again, this is very large scale. This is another figure of a similar phenomenon we've been talking about. We kind of get our bearings. You can see the Hadley cell. This is calling it the mid-latitude cell instead of the Farrell cell. That's fine. And we have the polar cell up there. So this is talking about kind of the descending air, not the descending air at 30 degrees north, not over land to give us a desert, but say it's over the ocean. What that actually gives us is kind of these very light winds over an ocean, and they're known as the horse latitudes. And if you're an animal lover, don't listen, because horse latitudes historically came with these diminished winds. They couldn't get from point A to point B so well, so they looked at ways to lighten their ship. And so one of the ways to lighten the ship was to turn the horses overboard. They're called the horse latitudes, I know, right? Well, let's look at the surface winds a little bit associated with the Hadley cell. Now, we learned this morning about this deflection to the right of large bodies of air, deflection to the right in the northern hemisphere. So here I have ascended, okay, I hit the tropopause, I came down, and part's going to go this way, deflection to the right, okay, yeah. That worked out fine. Deflection to the right. So at the Earth's surface, actually that's going to create what we call an easterly wind. So we're all about, you and I grew up saying, oh, I wonder what the weather's going to be like. Well, let's look at the map and see what's coming from the west. If you are between 0 and 30 degrees latitude, under the Hadley cell influence, you're probably going to look to the east to see what sort of weather systems are headed your way. So those are what we call the easterly trade winds, specifically in the northern hemisphere, the northeasterly trade winds. So then we kind of got this, the word is ITCZ. If I go back to a hot spot here, which is around the equator, but it wanders, okay? And actually, we're starting to finally get to where this ball can help us. Okay, see this right here? Okay. These actually are ocean currents, but what causes ocean currents are winds, prevailing winds. So we see kind of a north, we see sort of, well, we see winds from, or in this case currents, from the northern hemisphere and the southern hemisphere meeting up at what's called the intertropical convergence zone, which again, what's causing these ocean currents? Wind. So, okay. Well, let's go up one cell. I think sometimes it's got 2 L's and sometimes it has 1 L. I don't know. 1 R, 2 R's, I cannot spell. So the Farrell cell is near and dear to our heart because, yeah, we're in the Farrell cell. So we need to kind of pick up where we left off with the Hadley cell. This is the Hadley cell. We said this descending air, some of it goes this way, and the descending air, some of it goes this way. And then here's the deal. If you kind of picture, this is north, south, and so I guess we have east and west. Deflection actually is to the right, and so that's actually why we have a surface in the Farrell cell, which is we are. We do have a westerly wind. So they're called the mid-latitude westerlies at the Earth's surface. So if we go a little bit, if we have to go to the Hadley cell, we're going to have a surface easterly wind. If we go in the Farrell cell, we're going to have a surface westerly wind. And not to let the cat out of the bag, but actually if we go clear up to the northern, or clear up to the polar cell, we're actually going to end up with another surface easterly wind. All right, So the Ferrell cell, I said, you know, this will change seasonally and kind of what we have sort of surface features, but about 60 degrees, 30 to 60 is the limit for the Ferrell cell. So about 60 degrees, we have to have this rising or ascending air. And what do we know about rising or ascending air? It expands and cools. And it's kind of like with the intertropical convergence zone, a little bit, that this rising and cooling air can bring with it a band of precipitation. But it will be drier air in general and less precipitation. Okay, so it hits the tropopause, just like ascending air from the intertropical convergence zone, and part goes this way to finish the Ferrell cell, and part goes this way to start or be part of the polar cell. So polar cell, the way I think of the polar cell, I don't kind of pick up where the Ferrell cell left off. With the polar cell, I kind of look at, this has got to be the coldest conditions up here. And one of the things we know about cold is in your house, warm air rises, in your house, cold air sinks. Your basement's the coldest. So actually, and that's because the air is dense. So we have cold, dense air. It's kind of like, or for some reason, I picture cracking an egg on the top of the world, on top of the earth. And so that dense air is going to actually move along the Earth's surface in all directions. And as it moves along the Earth's surface, we can pick any kind of radial part, it's going to actually be deflected to the right, and that's going to give us an easterly. So I kind of think of that. I already told you we have easterly surface winds here, westerlies for us, and easterlies if you're between zero, if you're part of the Hadley zone. Okay. So we've gone, you have Hadley, Ferrell, polar cell. So polar cell, we have kind of that rising air that's kind of rises at the end of the Ferrell cell. It also rises with the 60 degrees, with the polar cell. It comes here and it falls, and you kind of see this was the cold, dense air. This is the North Pole. This is the cold, dense air moving away from the North Pole. Again, it's deflected to the right, which gives us another easterly. So, polar, Ferrell, Hadley. Let you fill those in. So it's kind of interesting. I mean, before there was even this necessarily a scientific method of discovery, science in general, folks were needing to get from point A to point B to point C to trade or for safety or for war. So they had to have a sense of these, what we call prevailing winds that were associated with what we now call the Hadley cells, the Ferrell cells, and the polar cells. Oh, the word is front. I think the video talked about this a little bit. So if we focus on these two cells, the polar cell and the Ferrell cell, actually we end up with these converging surface airs, okay? And this one's cold, and this one's relatively warm. I don't know, in Canada it seems kind of cold, but we have very cold and just cold. So we actually have, we talked about weather fronts and air masses with different temperatures meeting up, and we say that we use the word front to describe the transition between them. So we have a front here. It's called the polar front. And you can kind of see these clouds here, of course these clouds here, especially with the intertropical convergence zone. Okay, jet streams. There are actually at least a pair of jet streams. All a jet stream is a tube of fast-moving air. Okay, so here they are. And I like symmetry. Maybe some of you guys do too. So basically, our two jet streams in general go right here. One here and one here. Of course, I say two jet streams, but you're probably talking about, what do you think, 4 jet streams? Okay. So this is called the polar jet stream, and this is the subtropical. Yeah, I see 4 on there too. Fast moving ribbon of air. Now this says it may or may not go completely around the Earth, completely encircle the Earth, because honestly, how do I say this? If you're historically, we've had some awesome, brave people One set of brave people actually are into ballooning. Scary stuff. And if you're going to balloon across or around the world, okay, you're going to want to take advantage of this fast-moving ribbon of air. Okay, so you need to find those sweet pockets. And then sometimes if it's disjointed, you're screwed. Okay, so just kind of keep that in mind. Let's see, what else do we have? Subtropical jet is between the Hadley and Ferrel cells, and the polar jet is between the Ferrel and the polar cells. I like the video we watched because it kind of talked about these Rossby waves. And when I think about Rossby waves, I think about the jet streams. And to me, the Rossby waves in upper elevations are kind of driven by the presence of the jet streams. For instance, can you see where if the polar jet, we've had an Arctic air mass event recently, you know, if you have a jet stream that pulls air, you know, it helps move air masses down and it helps move air masses up. Actually, the polar vortex, which has been in the news, to me is a third sort of fast-moving ribbon of fast-moving air that kind of is up here, and if it weakens it, anyway. All right, what else do we need to know? So you're like, oh, what is this? Okay. Well, let's kind of get our bearings again, and you can see the 0 to 30, 60 to 90. So the dots are marking the three cells we've talked about. We have the Hadley, the Ferrel, and the polar cell. And at the Earth's surface, you can see NE stands for northeasterly trade winds. If you put easterly trades or northeasterly trades, westerlies, mid-latitude westerlies, and polar easterlies. So we do have kind of these interesting bands of ascending and descending air that creates kind of a semi-permanent fixture. I talked about the horse latitudes, and the horse latitudes, remember, were between the Hadley and the Ferrel cell. So there you go. There's your horse latitudes. What are horse latitudes then with this descending air between those two particular cells in both hemispheres? Well, we actually have two ascending regions, and that would be at your intertropical convergence zone here, kind of the equator, and also at where the Ferrel and the polar bump up. So we kind of have these general highs and these general lows. And here in a minute, we're going to look to see what that might look like on, this is a figure. Well, the next one's a figure too, but what would that look like if we were to kind of see what it looks like with regard to North America? So to me, when I think of doldrums, actually I think of similar horse latitudes. The doldrums, if you're in the doldrums, you're right here. You're between the two Hadley cells in the two different hemispheres. The word is cold here. Oh, I guess that's my crack in my egg. It just says that right at the poles in the northern hemisphere and southern hemisphere, you have that high pressure because that cold dense air coming down. All right, so the word is clockwise and counterclockwise. So this actually figure is kind of like this ball that I brought today. And it's showing you the prevailing winds, which to me matches up with the prevailing ocean currents. So I'm going to show you, this is January, and I'm going to show you July here in a minute. But this purple line, it's the intertropical convergence zone. It's the hot spot. And in January, you would expect the hot spot to kind of be in the southern hemisphere. I said maybe Tropic of Capricorn. We talked about movement in the northern hemisphere. Now these are winds, not ocean currents. Obviously, you can't have an ocean current over landmass. But we talked about around anticyclones or highs, winds are going to go clockwise. And around cyclones or lows, let's see if we can find a low. There's a low. Let's see. Maybe there's a low up there. It's actually going to go counterclockwise. So that's kind of that. Let's compare 6 months later and look at the wandering intertropical convergence zone. Yep, the purple used to be down here, and now the purple's up there. The intertropical convergence zone, we say, migrates where the hot spot of the sun is as the Earth, the tilted Earth actually orbits the sun. We're not going to get to it, but actually this wandering intertropical convergence zone actually gives us what we call monsoons. Can you see where a really popular monsoon is here in India? Check this out. Here's intertropical convergence zone with regard to India in January, and here's the intertropical convergence zone with regard to India in July. Opposite, the word's opposite. I think that's how far I wanted to get. Check this out. Yeah, I think that's pretty good. I think we're going to be good. So we're ready to, on Wednesday, go ahead and start our part 7, which will be severe weather. Okay? All right.